This is a photo of the sun. It might not look too impressive until you realize it was taken at night, not by looking up towards the heavens, but by looking down through the earth to capture a picture of the sun, which is located on the other end of the earth. This was accomplished by capturing neutrinos, which are subatomic particles emitted by the sun instead of photons of light. With that being said, let's dive into this fascinating topic of fundamental particles to better understand the science behind this picture. Okay, so today we're going to be doing fundamental particles or particle physics. And we're going to be starting with the Geiger-Marsden alpha particle experiment. So the main objective of this experiment was to investigate the structure of the atom, specifically to test the hypothesis of an atomic nucleus proposed by Ernest Rutherford. Back in 1897, when scientists believed in the Thomson atomic model, also known as the plum pudding model, where it was believed electrons were evenly distributed within a positively charged sphere. But that wouldn't last for long, because in 1911, Ernest Rutherford, a physicist from New Zealand, postulated that atoms have a very small but very dense nucleus with electrons orbiting around it. Therefore, to test his theory, he devised the Geiger-Marsden experiment, which is what we will be exploring right now. In this experiment, we have a particle gun with a box encasing a radioactive isotope to generate a beam of alpha particles, similar to a laser, which is then shot towards a gold foil that's 1 atom thick. The observation from this experiment was that the majority of particles beamed towards the gold foil pass straight through the foil with little to no deflection. However, the number of deflections decreased as the angle of deflection increased. What this means is that a small substrata of particles deviated from the original path and struck the fluorescent screen at different angles, hence proving that the alpha particles were being repelled by something within the gold foil. However, if the Thomson atomic model were true, the beam of alpha particles would simply not pass through the gold foil. So this experiment proved that Rutherford was in fact correct. So, in this diagram, the gold balls represent the gold atoms, and the lines depict the beams of alpha particles. It's evident that the majority of the beams pass straight through the atoms, but when they encounter the nucleus, represented by the white ball, the beams deflect at an angle. This is what's happening in the Geiger-Marsden alpha particle experiment. And we can record this by seeing the fluorescent screen glowing, and that is the end of the Geiger-Marsden alpha particle experiment. Now, as previously mentioned, the particle gun contains a radioactive isotope. So, now, let's dive into this topic and explore what are isotopes. Well, an isotope is basically just a nuclei or a nucleus that has the same number of protons, but different number of neutrons. This creates an instability in the nucleus, making it decay into something much simpler, much more stable. As a result, we have 2 kinds of decay. We have the alpha particle decay, and we have the beta particle decay. So the alpha particle decay is when an unstable isotope decays to produce a simpler, more stable element, and an alpha particle, which is basically just a helium atom stripped of its electrons, leaving behind the nucleus. So let's do an example of an alpha particle emission, we have radon 220 with a proton number of 86. Now, radon decays to produce polonium, and an alpha particle, which is just our nucleus of a helium atom, so 42 helium. Now, to calculate the values for polonium, we simply need to subtract 4 and 2 from 220 and 86. Because it's just basic math. We have a basket with 4 apples, and someone removed 2 apples from it. That means we now have only 2 apples left from the original basket. So that's just basic math. So 220 minus 4 is going to give us 216, and 86 minus 2 is going to give us 84. Therefore, polonium, the nuclear number of polonium is going to be 216, and its proton number, is going to be 84. Now, beta particle emissions. In this one, we have yet another radioactive isotope, which is going to decay to produce a more stable element, and an electron or a positron, which is basically just an electron that's positively charged. So let's just do an example to get a better understanding of this. We have thorium 225 with a proton number of 90. Now, thorium is going to decay to produce palladium and an electron. Right. So now, what do? We simply subtract this -1 to 90. So 90 minus -1 produces 91. The nuclear number of an electron is 0, so 225 minus 0 is simply 225. So our nuclear number of palladium is going to be 225, and the proton number is going to be 91. Also, you can write this equation like this: 225, 90, thorium plus so the electron can be written as a beta particle, whichever suits you. Both of them are correct in exams, so we now shift to fundamental particles. In ancient times, an ancient Greek philosopher named Democritus was the first to theorize the existence of atoms. However, back then, it was believed that atoms could not be split into further particles until we began smashing atoms in the Hadron Colliders. We now know that the universe is made up of these basic building blocks called quarks, which are what makes up atoms. We have 6 types of quarks named the up, charm, top, down, strange, bottom quarks. And just like in Stranger Things, we have an upside down, where everything is inversed, allowing the existence of 6 antiquarks, notably the anti-up, anti-charm, anti-top, and so on. With that being said, we now explore the proton and the neutron. These particles can be broken down into 3 fundamental particles: the up quark and the down quark. Both of them have the same flavors of quarks. A proton is made up of 2 up quarks and a down quark,
and a neutron is made up of 2 down quarks and an up quark. So let's just calculate the charges of both of the proton and the neutron. So a proton is made up of up quark, and down quark. We know that up quarks have a charge of plus 2/3, whilst down quarks have a charge of minus 1/3. So plus 2/3 plus 2/3 minus 1/3, and that should be giving us plus 1, which is in fact the charge of a proton. Now for a neutron, we have 2 down quarks. We're just going to rewrite this. We have 2 down quarks and an up quark. Therefore, our charge would be minus 1/3 plus 2/3, and that gives us an overall charge of 0. And that makes sense because neutrons are neutral. Great. Now, I'm just going to rewrite our thorium decay from the beta particle decay. So we had 2 to 5, 90. Right. So in this example, we can see that
Palladium acquired a proton which seemingly appeared from nowhere. Where did this proton come from?
well, this is what we're going to be studying here. So a neutron in thorium changed into a proton in palladium. This is why we somehow acquired a proton over here. It's simply that a neutron changed to a proton, and this changed produced an electron and an antineutrino. But if this decay went the other way around, where a proton changed into a neutron, then we would get a positron, which is a positively charged electron, and a neutrino. Now, this is what happens in the sun.
And this diagram represents the penetrating power of the particles we've studied so far.
As we can see, neutrinos are the most penetrating. In fact, they cannot be stopped but slowed down with water. So,
to capture the picture of the sun at night, we had to build an observatory deep underground with a massive water basin, so we could record the interactions of neutrinos
as they pass through water. This is how we took the picture of the sun. Now, we have a family tree of particles. We have the hadrons and the fermions. The hadrons can be broken down into mesons and baryons. Mesons are composed of pions and kaons, whilst baryons are composed of protons and neutrons. Whilst fermions can be broken down only into leptons, which are composed of
electrons and neutrinos.
So you need to learn this table. Now, let's explore pions and kaons. Pions and kaons
produced when cosmic rays, which are high-velocity atomic nuclei or protons, strike our atmosphere to produce a rain of subatomic particles, amongst which are the pions and kaons.
Pions are made up of an up quark and an anti-down quark, whilst A kaon, which is negatively charged, is made up of a strange quark and an anti-up quark. So, the way I like to remember this is the Nintendo DS. And this DS over here is sandwiched by two U's with an alternating anti. So we have normal, anti, normal, anti. So then this is our cation and this is our kaon. Great, so now we can move on to past paper questions. Okay, so in the first question we have a sodium nucleus or isotope that's decaying to produce a beta plus particle, which is an anti-electron or a positron. So state the name of another lepton that's produced. Remember, leptons are electrons or neutrino. When a positron is produced, we will get a neutrino. So it's neutrino. Determine the nuclear number and the proton number of the nucleus that is formed by the decay. So we have 2211 sodium decays to produce X plus, or positron, which is plus, plus 0 plus 1 beta plus. Now, the nuclear number of X is going to remain as 22, whilst we are going to subtract 1 from sodium. So it's going to become 10. Nuclear number is going to be 22, whilst our proton number is going to be 10. Describe the change in the quark composition of the nucleon. It's going to be an up-down quark changing into a up-down quark composition. So an up quark is going to change into a down quark. Great. So now we need to calculate the charge in terms of E of a baryon. Remember, a baryon is either a proton or a neutron. So we usually do this approach. U, anti is equal to 2 over 3 plus 2 over 3 plus 2 over 3. And this gives us 2, whilst all the down quarks are going to be minus 2 over 3 minus 2 over 3 minus 2 over 3, which is going to give us minus 2. So the general charge of each quark is going to be minus 2 over 3. Basically, the reverse of this. State a possible flavor type of the quarks. Well, it's up, anti-up, anti-up, anti-up. Moving on to the second question. An unstable nucleus decays by emitting beta particles. Determine blah 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 the charge in A and the charge in Z. So A Z X produces F beta minus. So we know the change in A is going to be 0 because a beta particle has 0 as a nuclear number, whilst having a minus 1 as its proton number. because it's negatively charged. So we know that the change is going to be Z plus 1. Plus 1. The change in A is going to be 0 because there is no change. The nuclear numbers is going to be A, Z plus 1. That's it. State the name of the lepton that's emitted. It's going to be an antineutrino. So, antineutrino. A particle P is composed of an up quark and an anti-down quark. Calculate in terms of E the charge. So we have an up quark and an anti-down quark, which is going to be plus 2/3. Usually, a down quark has the charge of minus 1/3. Well, an anti-down quark is going to be plus 1/3. So, plus 1/3 is going to give us plus 1e. So, plus 1, that's your answer. Particles P belong to two groups of particles. State the names of these two classes. Particle P. Okay, particle P. The two classes are hadrons and mesons. Okay, so number 3. We have cesium that's decaying to form X. That's decaying to form element X with an antineutrino and an electron or a beta particle. Now we need to state the numbers represented by each of the following letters. So P is going to be 0 because an electron doesn't have a nuclear number. Q is going to be 137 because there is no change to the nuclear number when there is a beta decay. R is going to be -1 because an electron is negatively charged. And S is going to be 55 plus 1 is equal to 56. Now, great. State the name of the class of particles that includes the beta particle. That would be lepton. The particle Y has a quark composition of D, where D represents a down quark. Okay, show the changes. Show that the changes of particle Y and Z are equal. Okay. So D, that's a lot of D's, is equal to -1/3 -1/3 -1/3 is equal to -1e. That's the charge of all these 3 D's. And now we have anti-up and a D. It's going to be -2/3 -1/3, which gives us -1e. So the changes are equal because the charges are equal. So shown. State and explain which particle is a meson and which particle is a baryon. So the meson is going to be the double quark composition, and the baryon, which is usually a proton or a neutron, is going to be the triple quark composition. So the meson is going to be the anti-up and down quark, whilst the baryon is going to be the down, down, down quark. Therefore, Z. Therefore, Y. Okay, so we have a particle P that's decaying to form a nucleus Q and an alpha particle. Okay, the mass of nucleus P is 243 U, and the helium or the alpha particle is 4U. So the mass of Q is going to be 239U. Great, 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 great. Now, right, so we need to explain why using the principles of momentum, we need to explain why the velocities are occurring in a different direction. And that would be because the total momentum before the decay is zero. Nucleus P isn't moving, it's just right there sitting. So its momentum is zero. And in order to have a total momentum of zero, we need to have the products traveling in the opposite direction. So total momentum before decay is zero. Therefore, nucleus Q and alpha particle have momentum in different directions. Determine the initial speed v of nucleus Q. So that would be m1 v1 is equal to m2 v2. Right. We know that the speed of the alpha particle is 1.6 times 10 raised to the power of 7. We also know the mass. So 239 U is equal to, U times V1 is equal to the mass of the alpha particle, which is 4U times its speed, which is 1.6 times 10 raised to the power of 7. We can cancel the U's, and that would give us V is equal to 2.7 times 10 raised to the power of 5. And that's your answer. Okay, so we now need to calculate the kinetic energy of the alpha particle in MeV, which is mega electron volts. Ek is equal to half mv square is equal to half times 4 1.66 times 10 raised to the power of negative 27. This value here is U. You should be having that in your formula sheet. And times the velocity, which is 1.6 times 10 raised to the power of 7 squared. That will be giving us 8.5 times 10 raised to the power of negative 13 joules. We also know that 1 electron volt is equal to 1.6 times 10 raised to the power of 19 joules, and 1 mega electron volts is equal to 1.6 times 10 raised to the power of negative 13 joules. So our kinetic energy in MeV is going to be 8.5 times 10 raised to the power of negative 13 divided by 1.6 times 10 raised to the power of negative 13, which is going to give us 5.3 MeV, and that's your answer. Okay, so the last part, of course, representing nucleus P, okay? A nucleus R has a nuclear number of 242 and is an isotope of nucleus P. Nucleus R decays by emitting beta particles to form a different nucleus S. Okay, we need to show this. Right. So we need to find the nuclear number of P, which is going to be 95 plus 148 is equal to nuclear number, which is going to give us 243 nucleon. So the difference between R and P is simply 1. So R is going to be found here. R. Now, R decays by beta particle emission to form nucleus S. So R 243, and our proton number is 95. 95 decays to form S by beta particle emission. Okay, so our nuclear number is going to remain the same, but our proton number is going to increase by 1. So 95 plus 1 is equal to 96. So 96, 243 minus 96 is equal to 146. There. That's S. Okay, so state the name of the other lepton in addition to the beta particle that's emitted. That would be an antineutrino. So antineutrino. There. With that, we conclude fundamental particles. I'd highly recommend going through the worksheet that I've uploaded in the description of this video and work out all the past paper questions in there. Make sure you nail it. It's really easy to score full marks in here. You just need to learn some things, and I highly recommend doing that by using mnemonics. But yeah, good luck, and thank you for watching my video.